Hi everyone, Robin here again with part 3 of lecture 4 on Popan models. This time we're going to be talking about Popan model fitting and the Popan lambda model. And before I start that, there's some more typos and clarifications from part 2. So I'll show you those. So starting with slide 7, and this is probably the most important one. I've been talking, maybe switching back and forth between talking about these parameters at different times or at different surveys. And so I think all of the explanations I've been giving apply when there's been a survey at every time. But of course, that's not always true. Like in the Maui dolphin data set that I showed you, there were sometimes different length gaps between the surveys. So actually, most of what I said applies either way. You just need to realize that these parameters there'll be one for every survey generally. But the only major difference is the survival probabilities. So if you have a survival probability that applies between two surveys, but there's been multiple time periods between the surveys, you should understand that survival probability to be the product of the survival probabilities for each of those time periods, right? And then that will be different depending on the length of the gap between the surveys. So I'll talk about that a bit more towards the end of this part, but you can let me know if that's too hard to understand. On slide 8, I just fixed this from subscript from t to t-1, as I mentioned in the recording. And in slide 9, I just made it clear here that this final chi parameter refers to the probability of not being observed after time t+1. And then in this expression for the capture history probabilities, I think that my notation was not clear enough before, so I've changed it a bit. So what this is expressing is that if the animal was captured at time t, then you'll include the capture probability for time t in the likelihood. And if it was not captured at time t, you would, this is between the first and last captures, then you would include the term 1 minus the capture probability at time t. And so I'm just expressing that by using this set C prime, which is the set of all occasions when an animal was not captured. And so still using this identity function. So here saying that if the animal was not captured at time t, so t is a member of the set of times when it was not captured, then this identity function will be equal to 1. And so this term will be included in the likelihood. Otherwise, this identity function will be equal to 0. So this term will become 1 and will just disappear. And then I just made this explanation a little more clear for this example capture history 1,1. So the reason this capture history has this expression is that it was first captured at time 1, and then it survived and was captured at time 2, and that was the last time it was captured. Okay, and my email's there again if anyone has any questions or feedback. I'd be happy to hear it. Okay, so Popan model fitting. The Popan model is fit using numerical optimization to find the maximum likelihood estimates. So you would write the code to calculate the negative log likelihood from the data in terms of the parameters. And then you would call an optimization function which will find the parameter values giving the minimum of the negative log likelihood. So the reason we use minimization is just a convention for optimization. That's why we take the negative value and minimize it. And then we use logs because the likelihood is expressed as a product of lots of independent probabilities. And that product will get very, very small. So it's impossible to represent such a small number accurately in a computer. So we take logs, and that turns the products into sums and avoids that, that problem. So by default, numerical optimization works by evaluating the objective function at multiple combinations of parameter values, and it uses the value of the function at those different parameter values to figure out in which direction the function is decreasing in terms of the parameters. And then it'll follow that direction to find the minimum. There are various R functions for this. NL, MinB, and Optim allow you to set constant bounds on the parameters, which we'll need for the probabilities so that they can be bounded between 0 and 1, and also for the superpopulation size so that we can bound it to be greater than 0. Constructum allows you to also set bounds on parameters in terms of other parameters as linear functions. And so I'll mention that again towards the end of this part. So the optimization functions report parameter values and whether or not they think that they've converged to a minimum. They can also return a numerical approximation of the Hessian, which is the second derivative matrix of the negative log likelihood at the supposed minimum. That matrix is called the empirical Fisher information matrix. And it's special because the inverse of that matrix is the covariance matrix of the maximum likelihood estimates, which gives us the estimates of the standard errors that we can use to create confidence intervals. So I've just shown you this is, what a Hessian would look like for two parameters, x and y. So we've got the second derivatives of the negative log likelihood. And so you can have the unmixed and the mixed second derivatives there. And when you evaluate this Hessian at the minimum of the negative log likelihood function, that is where you take your parameter estimates, and you take the inverse, then you get this covariance matrix for the for your estimates. And so on the main diagonal, you'll have the variances of each of your estimators. And if that seems like magic, it pretty much is. But intuitively, the Hessian, as it's the second derivative matrix, it represents the curvature of the likelihood surface. And the greater the curvature, the more precise the estimates and the smaller the variance. So I've tried to illustrate that here. These are plots of the negative log likelihood just over one parameter. And you can see the minimum in both cases is at 0. but this one has much greater curvature at 0. So it's curving upward, so it has a high positive curvature there. And this one has smaller curvature. And you can sort of see intuitively how this kind of likelihood surface would give you more precise estimates. You're going to be, there's going to be less variance in your estimates here than there would be here. I hope that's intuitive. For nonlinear functions with many parameters, numerical optimization can be slow, inaccurate, and unreliable. So we're renaming the optimizer function optim to suboptim. But it works much better when you also have the functions for the gradient and the Hessian with the objective. And then you can, so that's because the optimizer can then use the gradient and the Hessian to know in which direction to go in order to decrease the value of the function. And it can also evaluate the gradient directly to tell when it's 0, the gradient has to be 0 at a minimum. Then you can also evaluate the Hessian at the minimum analytically. So instead of getting the numerical approximation of the Hessian from the optimizer function, you can just evaluate it, given that you have the function of the Hessian. For simple models like Model MT, we can actually derive these functions, these derivative functions, and just code them up manually. And I'll show you that you can actually see that in Rachel's code. So this is Rachel's code for illustrating Model MT. And if we look at mt.fits.func, you can see the negative log likelihood function is here. And she also has the grad.func and the hess.func. So because Model MT is a relatively simple model, you can just analytically derive the gradient and the Hessian, and then you can just write the code to evaluate them. Oops. Close that one. Okay, so for Model MT, you can just code up the gradient and the Hessian, but for Popan models, those functions are extremely complicated, largely due to the recurrence relations. In general, the only practical approach is to write the likelihood function in a format that allows for automatic differentiation. So for example, there's the TMB package in R. So if you use this package, you can write the code for the likelihood in a C++ file. And then the TMB package can automatically find the derivative of that likelihood function, even though it would be a huge and extremely complex function that you would never want to write down. The computer can still use it to find the values of the gradient and the Hessian. We don't have time to go into that in detail, but I would say that if you are trying to optimize a function of more than 3 parameters, you'll never really know if you've found the minimum unless you have the gradient somehow. And I'd recommend TMB. Someone asked in the office hours, the Zoom office hours on Monday, about the difference between rmark and marked, the 2 different packages in R. My understanding is that marked was written later to use TMB to fit CJS and JS models, including Popan. So I would recommend using marked out of those 2 different packages. But if you're fitting Popan models, you can also check out the next lecture on Kapow, which also uses TMB. So when you're writing your code, you should try to do as much of the computation as possible outside of the likelihood function, because the optimizer is going to be calling the likelihood function over and over. So you don't want it to be repeating computation, which it doesn't need to. For model MT, the data can be summarized by the numbers n sub j of animals caught on each occasion j, together with the total number caught, n. This was actually shown in lecture 2, but this sort of shows you how it works. When you take the product of all the capture histories, and each one just contains the capture probability for each occasion when the animal's captured, and the non-capture probability for each occasion where it's not captured, this product just simplifies to, for each capture occasion, each survey, the number that were captured on that occasion, that's the number of times you have to multiply this capture probability. And for the non-capture probability, you're just using the rest, so the number of animals that were not captured on that occasion. So this actually shows that those numbers, the numbers captured on each occasion, together with the total number captured, are actually another sufficient statistic for model MT data. And we can see this in Rachel's code as well. So this is the mtfit.func. And the first thing that she does is find the frequencies. So this is, well, it's easier to see here. So it's the frequencies of zeros and ones, and she's applying it to each column. So for each column in the capture history data, she's finding how many ones and how many zeros. And so that's the numbers that were caught and not caught on each occasion. And I actually, this is actually what I was talking about when I said that these column sums, together with the total number captured, are actually, that's all that model MT really uses to make its estimates. So if you remember, we were comparing when the numbers captured in each survey were close to the total number captured, or when they were further away. And when they're close, it looks like we've got a high capture probability, and so the total number captured is probably closer to the total population. Okay, for Popan models, the data can still be summarized, but it's a little more complicated. So you still need the total number of animals caught in. And then, so just looking at the capture history probabilities, you have these terms psi sub f, and then the captures and non-captures between the first and last capture, and the survival between the first and the last -1. And then, yeah, did I mention this? The chi sub L parameter. So remembering that psi sub f is the probability of not observing the animal before its first capture occasion f, and the fact that it's in the population at occasion f. And chi sub L is the probability of not seeing the animal again after its last capture on occasion L, given that it's in the population at occasion L. So the numbers that you need to summarize this, these probabilities, capture history probabilities for all of the capture history, are just the numbers F sub j caught on first caught on each occasion, the numbers L sub j last caught on each occasion, the numbers caught and not caught, N sub j and M sub j, on each occasion from the first to the last captures for each animal, and the numbers S sub j known to be surviving from their first to their last captures on each occasion. And with those numbers, you can express the product of all the capture history probabilities with this term. So where you're just multiplying psi sub j for each capture history, for each surveyed j by the number first caught in that survey. And then this part is similar to for model MT, except that this number M sub j is the number of animals not captured in each occasion j between their first and last captures. And then we have phi sub j raised to the power of S sub j, so the number of animals surviving between their first and last captures in survey j, and chi sub j to the power of L sub j. So that might take a bit of thinking to understand. To find all those numbers, you just loop through all the capture histories, and for each capture history, find the first and last captures for each animal, and the captures and non-captures and survival in between their first and last captures. And you can keep all that data as you loop through and find the summary statistics. And again, these numbers form a sufficient statistic for Popan model data. That means that these numbers are all you need to find the maximum likelihood estimate. And then P sub theta, remember that's the probability of observing an animal at least once. And psi sub j and chi sub j have to be calculated inside the likelihood function. So you want to find these summaries outside the likelihood function and pass them in, because you don't need to recompute them every time. They only rely on the data. But these values rely on the values of the parameters, which the optimizer is going to be changing every time it evaluates the likelihood. So you have to calculate these parameters inside the likelihood function based on the parameter values that will be passed in by the optimizer. And psi sub j and chi sub j, remember, are calculated from recurrence relations. And to do that, you just use a loop. So you define the base case, and then you would loop through finding the next value from the previous one and the other parameters. And I'm thinking I'm not going to show you my code for doing this because I'd like to make it part of the assignment. But I will give you lots of hints in the assignment so that you can go through it step by step. But I think you should be able to calculate the Popan likelihood and fit the Popan model yourself to a particular data set, just in a simple case. So I think that would be a really good exercise for the assignment. Okay, we want to take logs to find the log likelihood. And like I said, taking logs just turns the products into sums. And remember that you can take the exponents down in front of the log. So the log of this whole term here is just the log of the first part multiplied by the exponent. So hopefully you know how logs work pretty well. And then this term here, remember this is just the binomial coefficient, and R actually has functions for finding binomial coefficients, so the function is choose, and there's a log version, just L choose, so you can just use that function. Very handy. Base R has so many handy functions. And optimizers usually use continuous parameters. So they'll be passing in continuous values for n sub s, not just integers. But that's okay because these functions also work for continuous inputs. And if that doesn't make sense to you, you can Google the gamma function, which is like a continuous extension of factorial functions. And so these functions are extended to continuous inputs because they're based on the gamma function. Okay, parameter identifiability. If you remember, CJS models have problems with parameter identifiability, and Popan models have the same problems, but also more problems. So, as described in lecture 3, in general, you can separate the event that an animal survives from one time to the next, so it is not captured then, from the event that it does not survive over that interval. Because the animal could be captured later. And so if it's captured later, you know that it actually survived but was not captured in between. And that allows us to separate phi sub t minus 1 from p sub t. So the probability of surviving from time t minus 1 until time t, and the probability of being captured at time t. But an animal cannot be recaptured after time k, the last survey, so you can never actually separate phi sub k minus 1 from p sub k. You can never really tell if an animal survives to the last time but is not captured there, or just died for the last time. And that means that we can't actually estimate these parameters separately. We also can't estimate the entry probability for survey k, because we can't tell how many animals survived from time k minus 1, and so we can't tell how many animals enter at time k. So we can't separate these. Likewise, we can separate the event that an animal enters the superpopulation at a certain time but is not captured then from the event that it enters earlier, because the animal could have been captured earlier, and then we would know that it had entered earlier. That allows us to separate p sub t from p sub t, so the entry proportion for time t from the capture probability at time t. But an animal can't be captured before time 1, so we can't separate the pent parameter for time 1 from the capture probability at time 1. And that also means we can't estimate the pent parameter for time 2, because we can't tell how many animals enter at time 1 and then survive till time 2, so we can't separate that from how many enter at time 2. Basically what this is showing is that the full Popan model has more parameters than can actually be estimated from this kind of data. And these are just the analytic problems. So these are just the problems that apply for any data set. You can never have a data set that would let you estimate all of the parameters in the full Popan model. But for some data sets, you might just not include capture histories that allow you to separate these kinds of variables at particular times apart from the first survey and the last survey. And so any model that still includes those combinations of parameters will not be identifiable for that kind of data set. Mathematically, what's happening is that the confounded parameters only appear in the likelihood as a product, and that means that there's no unique maximum likelihood estimates, because you can always raise the value of one parameter and lower the value of the other and get the same value for the product. And so there's no unique maximum, right? You could have infinitely many different combinations of those parameters. This is what I'm trying to illustrate what a likelihood surface looks like. So this would be a negative log likelihood surface. When there's no unique maximum, no unique minimum, you can see that the surface is coming to a minimum at a line or a curve through the parameter space. So anywhere on this line would be a minimum, but these represent completely different parameter values. So it's impossible to estimate to choose between these parameter values. This is just a section cut out of this surface to illustrate if your parameter bounds were, if the minimum of your likelihood surface actually occurs at the boundaries of the parameters. So, for example, for a capture probability, the lowest value it can take is 0, and so your likelihood surface might approach a minimum at that boundary at 0. So when you have a non-identifiable model, what should happen is that the optimizer should recognize, while it's trying to find the minimum, that there are multiple points where the likelihood is at a minimum, and it should report what's called singular convergence, which just means that there's no unique minimum, but there are infinitely many. And if you actually pass the gradient and Hessian functions into the optimizer, there's a decent chance that it will be able to do that, and it will tell you singular convergence. But there's also a chance that the optimizer will just find a minimum at one of the parameter boundaries. So like I was showing here, if the boundaries of the parameters stop it from finding the minimum, then it won't know that there is no unique minimum, but we'll just go to the minimum at the boundary. And if you don't pass the gradient and Hessian functions into the optimizer, it probably won't be able to recognize that there's singular convergence. So it will just sort of look around and find some minimum value, and it probably won't be able to recognize that actually there are infinitely many minimums. So in that case, it will just report convergence and give you the parameter values at some minimum, even though there's no reason to choose that minimum over any other. It's just that without the gradient and the Hessian, numerical optimization just doesn't work that well. So the point of all this is that you definitely shouldn't fit the full Popan model. Even if the results are good, they're basically random. And that means that you have to either estimate the product of the confounded parameters instead of the parameters themselves. So you have that product term in the likelihood, and you can estimate that. Even though that product generally won't have any specific biological meaning. It's just a mathematical term. And if you choose to estimate that, you can estimate all your other parameters properly. Or you can constrain some of the parameters to be equal or to specific values if you think that you know some likely values for those parameters. So as James mentioned in lecture 3, you can constrain capture probabilities at the start or at the end of the study to be equal if you think that those studies probably had similar capture probabilities. You could also constrain the survival probabilities to be equal if you think that the survival probabilities probably aren't changing over the course of the study. When you fit your model, you should always check for boundary estimates, especially 0 or 1 for probabilities. If you have boundary estimates, it's a good sign that you probably have a parameter identifiability problem, either from your model having too many parameters or just because the data is not good enough for that model. If you see strange estimates or strange variances of your estimates, you should be suspicious that you might have an identifiability problem, and you can check both of these cases by fitting a simpler model and see if the estimates improve. And the biologists will know more about what's realistic for their particular study, and they have their own conventions about how to check for these kinds of problems, so you should listen to them. Okay, Popan lambda models were developed in 2013, or first published in 2013 by Carroll et al., my supervisors, and they constrained the entry proportion parameters so that the population follows a smooth growth curve, given by the growth rate lambda, which is equal to the ratio of the expected population sizes. So the fraction of the expected population at time t+1 divided by the expected population size at time t. So this is the factor by which the expected population size has grown from time t to time t+1. When you constrain these parameters so that the population is growing at a constant rate, you also should constrain the survival probability to be constant throughout the study, because otherwise you'd be saying that the survival probability can go up and down, but the population growth rate is constant, and that means that the birth rate for the animals would be going up and down exactly opposite to the survival rate. And that's a strange thing to say, right? So in these models, you usually also constrain phi to be constant throughout the study. Once you fit a Popan lambda model and estimate lambda, you can calculate the entry proportions using this relation, this expression. So if you set the first entry proportion to 1, and then you can define all of the other entry proportions for t greater than 1 using this expression. And once you've done that, you can divide all of them together by the sum of all of them together, and that will give you proportions. The reason this expression makes sense is if you imagine the population. In the first survey, the entire population is exposed to capture for the first time. So all N animals enter the superpopulation at time 1. Then in the next survey, only the newborn animals enter the superpopulation. And the newborn animals are the population growth rate multiplied by the population size minus the survival probability multiplied by the population size. So that's the new population size minus the number of animals that survive from the old population size. So that's just the new animals, newborn animals. And then at the same time, in the second survey, the size of the population grows to lambda n. So each time for each new survey, you have the newborn animals entering the superpopulation, and the number of newborn animals will be equal to lambda to the power of t minus 2 times the population size. I've got this here. So at time 2, you have lambda minus phi times n animals entering the population, and the population itself increases to lambda n. And then at time 3, you have lambda minus phi times now lambda n animals entering the superpopulation, and the population increases to lambda squared n. And that just repeats at every survey. And we don't need the n in the expressions above because at the end you have to divide them all by their sum, so the n's go away anyway. And just repeating what I said at the start of this recording, I'm assuming that there are surveys at every time, but if there are gaps, you just have to remember that the values of lambda and phi should be raised to the power of the number of time periods between the surveys. So if there is a gap of 2 time periods between 2 surveys, the population would grow by lambda in the first time period between the surveys, and then by another factor of lambda before the second survey. So you just have to remember that when you're making these calculations and there are survey gaps. And the same is true for phi, as I mentioned at the start of the recording. So the Popan lambda models are very parsimonious because they constrain all of the entry proportions to fit a smooth growth curve, and they constrain all of the survival probabilities. But these constraints are often reasonable if you think that there's no reason that the population growth rate would change significantly during the study. So this is common where you might have a population that was reduced a lot, but then has been protected and is recovering. And in that case, you often would want to estimate the rate of recovery, so the population growth rate itself. So this kind of model can be very useful. And because it's so parsimonious, it can be identifiable even for very small data sets in very challenging conditions. For example, where there's low survival or low capture probabilities. When there's low survival, it's hard to recapture the same animals, which means that your data sets are less informative. They also do not constrain the capture probabilities. So you still could constrain these capture probabilities, but I think that often these would be the hardest parameters to constrain because you don't really have any, you might not really have any idea what the capture probabilities are or which ones would be equal. So, but you don't, because you're constraining so many other parameters, you don't really have to constrain the capture probabilities for a Popan lambda model. Okay, so that's the end of the section on Popan models. The next lecture I'll be talking about Kapow, which is a web application for fitting Popan models and performing power analysis. So I've prepared some exercises for you to try to understand the material from this lecture better. So I'll just go through them now, and then I'll probably go through the answers to them in the Zoom office hour on Monday. So the first one is to write down the capture history probability for this capture history, 01010, for model MT and for Popan. And then, so you're just going to write it down in terms of the parameters, and then compare the two expressions and try to write down in words what's the difference between them and what the difference means, so why they're different. For this exercise, you're going to do maximum likelihood estimation for the probability in a binomial distribution. So you start by writing down the expression for the negative log likelihood of the binomial distribution, and then write an R function to compute that value, the negative log likelihood. So it'll have three inputs, P, N, and X. So this is matching the definition of the binomial distribution from the first lecture recording for lecture 4. And you should just make sure that P is the first input into your function, because that's the parameter we're going to optimize. And the optimizer always assumes that your parameter is the first input. Make sure that it works for some reasonable input values, and just try some different values and see if you can understand when the value is the largest, or I should say the smallest, because it's the negative log likelihood. And then try to use NL-min-B to find the maximum likelihood estimate for P. So you can use the starting value of 0.5. Remember, P is a probability, so it has to be between 0 and 1. And you'll need to specify that in the bounds inside the call to NL-min-B. And pass in the values n equals 100 and x equals 50. That will be like your data. Right? So P will be your parameter, and these values will be your data. So if you had a group of n objects and it was divided into 50-50, you can think about what value of the probability of classifying each object to each group would be the maximum likelihood estimate. You'll probably need to read the help for NL-min-B, so you just run $NL-min-B in R and it'll show you the help. And once you get it working, check that the convergence code is 0, which means success. And the maximum likelihood estimate should be x over n. And then try it with these different values of x. And then for this exercise, you can imagine that you fit a Popan lambda model and you get the results n sub s equals 1000, lambda equals 1.05, and phi equals 0.95 for 10 consecutive surveys. So a survey at every time period. And you should try to use R to find the pent parameters using the expressions that I've told you in the lectures. And then you can use these pent parameters with the survival parameters to find the expected population size, NT. So in both of these cases, you have to find the parameters for all of 10 consecutive surveys. And in this case, you'll need to use a loop because it's a recursive definition. and then plot the values of the parameters over time and explain why the plots look the way they do. And I've included a challenge exercise. I think this one will be pretty difficult, but it's to use constructum to find the MLEs for the probabilities P sub I for a multinomial distribution, which divides 100 objects into groups, 3 groups of sizes 20, 30, and 50. So now this will be similar to the binomial case, but you'll need to change the likelihood to a multinomial likelihood for 3 groups. And then I'm telling you to include these numbers as your data, and you'll have 3 probabilities as your parameters. Just a heads up, don't use starting values of 1/3 for each of your 3 probabilities, because 1/3 is not represented exactly in a computer, and if you add 1/3 3 times, it's greater than 1. So this will give you an error. You can just use 0.33. And then once you get this working, try some different group sizes and see if you get what looks like sensible maximum likely estimates for these probabilities. I think this will be pretty tough, so only do it if you're interested. So that's all for this lecture, and I'll see you in the recording for the first part of lecture 5.